So the first method of apportionment that we're going to deal with is Hamilton's method. Now, this method is fairly easy to describe because we're going to use a standard divisor again. So basically how Hamilton's method goes is we use the standard divisor and we get all of our quotas. Now, we start by calculating the lower quota. That is taking everything down to the next lowest integer. And then after that, we give every district the lower quota. And we're going to have extra representatives left over because we rounded or we moved everything down. So we start by giving the extra representatives to the highest level of decimal and working our way down until we finish out giving all of the representatives. Now, when I say highest decimal, I mean the district with the highest fractional component remaining on the quotas. So let's take our example of 100 representatives. Now, first off, we have to start out by getting the standard divisor. So we want to take all of these things, add them together, all of the population, add it together. This was actually the one we previously did in the introduction. So we know that the total population is 100,000. Let me write that down. 100,000. And since we want 100 representatives, take 100,000, divide it by 100, and we get our standard divisor to be 1,000. Ooh. So each of these districts, we give the quota. So we have 38.343 when we round it. We have 21.23, 4.899, 20.405, 15.123. Those are the quotas we had. Our lower quota, obviously, take 38, 21, 4, 20, 15. Now, if you add those things up, 15 plus 20 plus 4 plus 21 plus 38, we have a total of 98 representatives that are going to be allotted. So we go and say, which one of these has the highest decimal? Well, if you look at District C, this 0.899 is the highest. And if we add a representative to the lower quota, so we make that 4 into a 5, then we're going to get 98 representatives now. So we need to add one more. And the next highest quota, let's see, 0.3, 0.2, that's 0.4, 0.6, is D. So the next highest would get an additional representative to make District D's number of representatives 21. Now, once we've done that, we've added 2 more representatives. We keep the rest of the representatives the same as the lower quota. So using Hamilton's method, District A would have received 38 representatives, District B would have had 21, C would have had 5, D would have had 21, and E would have had 15. Alright, so we're going to do the same thing with another example. And in fact, if you get the hang of this, you can pause the video and do this on your own and attempt this on your own. So I'm going to give about 5 seconds, and then I'll pick up again. Alright, so in this example, this second example, we still want 100 representatives. And if you actually go out and calculate the populations, 48,343, we've changed them somewhat. And so all of the same principles work here. So we're going to take our population, add it all up. Now, of these 5 districts, it turns out, again, we have 100,000 people. And so we have 100 representatives that we want. That means our standard divisor is, once again, 1,000. A nice even 1,000. By the way, standard divisors aren't always nice integers. Oftentimes, standard divisors will have decimal points and so on and so forth. Now, if we take 1,000, then it's fairly clear that our quotas, 48.3, pin's not right, 43, 5.610, 4.350, 30.349, and 11.348. So the lower quotas here are 48, 5, 4, 30, and 11. Now, calculate 48 plus 5 plus 4 plus 30 plus 11. And you see that we have 98 right now total representatives allotted. So we go back up and we look at which has the biggest decimal points. Now, again, in this case, this is slightly different here. B has a 0.6, and all of these other ones are fairly close, but the highest is C with 0.350. And so they'd each get an extra representative, although, in fact, these are awfully close decimal points. So, or excuse me, yeah, decimals. So in this case, the number of representatives using Hamilton's method is 48, 6, 5, 30, and 11. And if you add those up, 48 plus 6 plus 5 plus 30 plus 11, you'll get the total of 100 representatives, what you wanted. So, I want to change example 2, and all we're going to do is in the second example, instead of using 100 representatives, let's say we wanted to allocate 101 representatives. Now, this first part has not changed yet. We still have 100,000 total people in our population. But that does change the standard divisor. If you take 100,000, divide it by your 101 representatives, essentially you're going to get 990.099, and then it goes on and repeats. That's actually a repeating decimal, but basically you have 990.099 people per representative is what we're trying to get. So if we use that, we take the 48,343, divide it by 990.099. What we're going to see is we're going to get a certain quota. Now the quotas have changed because of the different divisor, and here's how they've changed. Quota for District A is 48.826. Let me write that down. 48.826. For District B, 5.666. 4.394. 393, depending on rounding. 30.652 and 11.461. So the lower quotas 48, 5, 4, 30, and 11. Now again, you can do this on, you should be able to do these things on your own at this stage in the game. So calculating and adding those things up, 48 plus 5 plus 4 plus 30 plus 11 is once again going to give you 98. Now this time, remember, we wanted 101 representatives. So we need to add to the 3 highest decimal points. So that would be A, that would be B, and that would be D. So in this case, the number of representatives using Hamilton's method would be 49 for District A, 5 for District B, for District C, oh, excuse me, gosh, I keep saying that, 6 for District B. C would have had 4. D would have had 31. And E would have had 11. So when you take 49 plus 6 plus 4 plus 31 plus 11, you get 101, which is exactly what we wanted to have. Now there's something that happened here between, again, these same populations on this slide versus the previous slide when we had 100 representatives. And I want to point that out. So on the previous 2 slides, we see that if you use 100 representatives, we had the following distributions of the representatives for the following district. So we had 48 in District A, and we had 6 in District B, and 5 in District C, and 30 in District D, and E had 11. What happened with 101 representatives, notice something a little bit strange happened. A got an extra representative. D got an extra representative. And C actually lost a representative. Now this seems a little bit counterintuitive that the number of total representatives went up, but for C, because of the way the rounding issues came out, C went from 5 to 4 representatives. Now this notation, this kind of idea, is called the Alabama paradox. And it was discovered a long time ago. You can check the dates in the book and look those things up. But basically, named after the state of Alabama. And in trying to allocate representatives one year, it was figured out that if you increase the number of representatives by 1, Alabama actually lost a representative. And this is an issue with this method. We can have the number of representatives total increase from 100 to 101, but a certain district may lose out, may lose a representative if we increase. Now, we'd like a system that didn't have that. We'd like a certain system where you would never lose a representative if you're in C's spot if the total number of representatives went up. But that just isn't the case in Hamilton. So Hamilton's has this Alabama paradox. Alright, so here's what I want. I want you guys to try, again, example 3 on your own. In this case, the total population is 10,000 people. So if you want to add that up, we want 100 representatives. And so you can figure out what the standard divisor means, what the quota means, and then how many representatives each of the districts would get. In this case, there are 6 districts rather than 5 as in the previous. And I want you to pause it, pause the video, try this on your own, and then start playing the video in about 10 or 5 seconds. I'll start back up. All right, so hopefully you've had a chance to do that on your own, and this is I'm going to do this very quick, and this is mostly in order just to be able to check your work. So we have 10,000 people, 100 representatives. That means standard divisor going to be 100. Let me write that down. Now with 100, quotas 25.95, 7.02, 9.92, 38.70, 5.73, and 2.68. So, excuse me. All right, so calculate, if you were given to everybody the lower quota, 25, 7, 19, 38, 5, and 2, you get 96. That means I need to allocate 4 more. In order of biggest decimal, A, C, E, D. Get the extra representatives. So, if I can write this down right, 26, 7, 20, 39, 6, and 2. This gives us the number of representatives of 100. That's what we wanted. Remember, and so with 10,000 people in this population, that's how the representatives would be allocated. Now here's what we're going to do. We're going to change the idea, change the population slightly. So we're going to add some to certain districts, and we'll see how that pans out. So again, we added some people to some populations. In fact, we had 78 people to the entire population. We kind of randomly put those in, and I want you to take this example, find the quota and the number of representatives using Hamilton's method for this example. Again, I'll give you about 10 seconds. Pause the video, do it on your own, and then come back and I'll finish it up. Alright, so you see that standard divisor in this case was 100.78. And when you actually go through and do the calculations, quotas here, and I'll write this fairly quickly, 26.146, 7.065, 0, 19.954, 38.42, 5.755, and 2.659. Now notice that I'm rounding to a couple of decimal points just so we can have some comparison. You don't need to, again, do infinite decimal versions. Round to a couple, and then if you need more, if there's two things that are tied at 0.954, then obviously you'd go beyond that. So we see that here, when you add these things all up, if you give everybody the lower quota, 26, 7, 19, 38, 5, and 2, we'd get a 97 as the total lower quota. So we have to add 3 more to get the 100 representatives we want. And in this case, the 3 that we would add to, we'd add to C, we'd add to E, and we would add to F. So C would get 20, E would get 6, F would get 3, and everybody else would have their lower quota. And if we allocated Hamilton's method this way, using the population of 10,078, then we get 26, 7, 20, 38, 6, and 3 representatives. Now this is slightly different than what we had in the previous slide. In fact, if you're real careful about this and look at it nicely, basically in the previous slide, D had 39 representatives, so in the previous slide, and F had 2 representatives. Now you might say, well, again, there's population change. But if you're real careful about looking at what population changed, then you notice that D actually originally had 3870, and F originally, this is in the last slide, had 268. So what we're saying is that the population, when we had 10,000 people, District D had 3,870. Now, it was allocated 39 representatives. The population actually increased by 2 people in District D. District F had 268 representatives when the population was 10,000. It did not change populations. So in fact, here, population in District D increased, while its number of representatives decreased. Population in District F stayed the same, while its number of representatives increased. Now, this is a little bit troubling because, again, it seems counterintuitive that one district would lose representatives while increasing a population, and another district in the exact same scenario would increase representatives while remaining the same. In fact, you can do this for different numbers, and you can get that one district increases, and the other district, you could have probably decreased this number by 1, and you'd probably still get the same result. So it's a little bit troubling. In fact, this is something that's known as the population paradox. That as population changes through the overall example, sometimes funny things like this can happen between two districts. They can swap a representative while in reality the population of one district is increasing and the other one's staying the same. Or in reality, maybe District D increased more than District F. And by the way, we didn't see, or we saw this happen. Again, it's a little bit troubling. Saw the Alabama paradox, but there's one other paradox which we'll get to right now. So we said that the Alabama paradox is basically when you increase the total number of representatives and we keep the populations the exact same for all the districts, but one district loses a representative. And that was called the Alabama paradox because, in fact, Alabama noticed this at one time in our history for obvious reasons. We saw the population paradox where we increase the total population, we keep the representatives staying the same, but a district which grows a lot maybe loses a representative, and a district that stagnates or doesn't grow as much gains a representative. And again, these things seem counterintuitive. Like I said, there's one other. It's called the new states paradox. And basically, if we add a new district, and the district has new representatives, so if we added on a district G to our examples before, and maybe all of the exact same, let's assume, for instance, G was allocated exactly 5 representatives. And we went from 100 representatives to 105 representatives. G was allocated 5. Everything else stays the same. Well, it is possible for 2 districts to actually, because of that extra 5 representatives, swap a representative. So a new district's added, let's say District G. They get their allocated representatives. But the other 2 districts stay the same population-wise, but one of them increases a representative and one of them loses a representative. That's called the new states paradox. Again, these are things that can happen in Hamilton's method. These sort of counterintuitive ideas. Now, one thing that I want to say about Hamilton's method that's nice is that each state is only getting either their lower quota, that's next lower integer, or their upper quota, next highest integer. So one of the nice things about Hamilton's is it's pretty straightforward and you have a systematic approach. The bad thing about Hamilton's is there's the availability of the Alabama paradox, the population paradox, and the new states paradox.